I'm going to talk about the covariant dynamics on momentum space, momentum and energy momentum space. So first, let me start with a little bit of introduction and context. Why do we study this? So in search for quantum theory of gravity, there has since some time been more or less consensus that the structure of space-time at the smallest scale has to depart somewhat from our usual continuum picture. So there are many different approaches how to modify space-time at these very small scales. Loop quantum gravity and different things in string theory, but there is also non-commutative geometry, which was developed as a mathematical disciplines related to quantum groups in the late 80s and 90s. So one approach that I'm following also is to arrive at the deformation of space-time at the smallest possible scale through the actually deformation of energy momentum space on very large energy momentum scales. So this idea was actually first introduced in the 40s by Snyder. His motivation back then was not, of course, quantum gravity, but he was actually searching for an alternative theory that would avoid the infinities that were appearing in then emerging field theory, quantum electrodynamics, and so on. And but the historical coincidence is that just about that time, Feynman and others, they patched things up, and later with the development of complete renormalization theory, this study was more or less abandoned on the West. But this interesting research did go on mostly through Soviet scientists. I'm sure the audience here will have heard about Mir Kasimov and Kadishevsky. Those are just a couple of names. There are also others. And of course, then and there's a whole body of work about this problematic from JETP journals and so on. But the things started to become fashionable in the 90s again in the Western science through the development, as I said, string theory, different approaches to quantum gravity, and so on. So the current state of affairs is that the mathematical properties of all these deformed spaces, symmetry deformations, and everything is very well established. That there is a huge body of research about it. What, in my opinion, is lacking is unified dynamical description. So even if we know that what happens with our symmetries and how do different operators behave in different contexts, we still don't know how do we describe the dynamics on this in these deformed cases. Or in other words, there are different proposals. The fact of the matter is, if you depart from the usual flat geometry of the energy momentum space, say as a first deviation from it, you may take it as a sphere. So in order to describe a sphere, you need one parameter, you need one scale, and that is the radius of the sphere. If you want to go to more complicated geometry, say an ellipsoid, then you need at least two, and so on. And the thing is, what you want to have is that once you allow the deformation parameter to vanish, or say if your deformation parameter is the radius of the sphere, you want to have sort of consistency condition that when you allow this sphere's radius to go to infinity, you want to go back to the original, to the canonical formulation of dynamics that we have. So this is formally written in the equation here. So here in this equation, so this P is, for instance, the radius of the sphere. And what you want to have is that your Hamiltonian, which is a functional of this P, or a function of P, once you put this radius of sphere to infinity, you want to go back to canonical Hamiltonian. But this, of course, is not unique. There is many things that you can add to your Hamiltonian, which will reduce to the canonical Hamiltonian in the original limit. So what I did is I proposed a formulation of dynamics that is covariant in the momentum space. That is, so in short, we take the usual formulation of the dynamics in momentum space. That can be field theory in relativistic case, or just say Schrödinger theory in non-relativistic quantum mechanics, and so on. And you take the standard formulation and you simply write it in a covariant way, in a way that can be applicable to any choice of coordinates and any choice of geometry of the momentum background on which you're doing your theory. And yeah, that's more or less it. That's the recipe, how I do it. This, of course, then leads to a unique formulation of dynamics. So let's see how it goes. So what I study is the the dynamics on maximally symmetric momentum spaces. So this is the spaces with constant curvature, and through a set of axioms. I mean, it's a little bit of abuse of language calling it axiom. It's just a list of demands, definitions, sort of the things that we want to have, our momentum space to have in order to have a reasonable theory. So first, like, you want to have energy momentum manifold that has a metric, that's a Riemannian. I mean, you don't want to do this Hausdorff spaces or stuff like that. So it's just reasonable stuff. Then the second manifold, there is a unique point, a unique origin. This is like the absolute origin, and the elementary particles are actually excitations above this absolute vacuum. There's also another set of exclusive points. These are called points at infinity. We can consider both infinite manifolds, so manifold without boundaries and manifold with boundaries. And I include these points at infinity for technical reasons, but they don't affect the dynamics of particles that are at finite distances. So the mass of particle is defined as a geodesic distance from the origin. And the two more axioms, I want to have two isometries allowed on this manifold. One is the isometry that leaves the origin invariant. So in a usual Euclidean case, so these are the rotations about the origin. And I want to have the group of isometries that leave the points at infinity invariant. So this would be like your translations in a standard case. As I already pointed out, I consider this a minimal set of physical reasonable requirements. And I also want to point out that less restrictive proposals have appeared in the literature, but they usually lead to theories with very, very different properties than the ones that we are used to. So let's say for the axiom 4, this is our usual Lorentz group. The physical origin of it is that we want all the observers and for all the momenta, we have to agree on the point of the position of the origin, on the point of the vacuum. This is why we need this isometry. For instance, the group in axiom 5. This is the group of translations or momenta addition. We want to have it. We wanted to have it an isometry because we demand that by if we have two particles of energy momenta P and Q, and both of these particles absorb, say, each absorbs a particle of momentum K, we don't want their distance on this energy momentum space to move. Why does it leave the points in infinity invariant? Because again, we don't want to be able to reach the point at infinity through any finite number of interactions. So some consequences of this is that our manifold P must necessarily be maximally symmetric. Otherwise, I cannot realize enough isometries on it. So these are the cases of flat space. And say if we are Euclidean, so we have a flat space, or Minkowskian, say we have a constant curvature which is positive, we have a constant curvature which is negative. These three possibilities are the only ones that are allowed through this set of axioms. Another point is, as I already emphasized, once I put this radius of curvature to 0, I want to be able to go back to the usual standard theory. This is also, this serves as an important consistency check. So everything I do with my theory, at every point I can put the radius of curvature to 0 and recover a usual case. A little bit, why do I take that the mass square is the distance of the from the origin? Actually, this is not my proposal. This has been circulated a long time. The idea is that there is nothing special in P squared per se, unless you're living in Minkowskian space. So you want to have it somehow coordinate independent and geometry independent. And it is only for the flat spaces that the points themselves are vectors. This is an interesting point. In all the other spaces, the points themselves are not vectors. Vectors are not P mu, but rather dp mu. So in order to generalize it, you have to have so you have to interpret this P square from the flat space as magnitude of or the distance from the origin over the geodesic. So the shortest path from the origin to a certain point. So, okay, let's start right into the non-relativistic quantum mechanics. First, we considered the case of the zero curvature, but we have a generalized coordinates as you have noticed, as you would have noticed from the set of axioms, there is no absolute definition of what energy momentum is. That implies that I am free to choose any sort of coordinates on this energy momentum manifold or momentum manifold for non-relativistic case and call them physical momenta. If not, then I would have to put in the axiom some specific ones. So we start with the usual canonical Heisenberg algebra. X's are the space operator, the position operators, and etas are here momentum operators. And your Schrödinger equation looks like a sum of the kinetic and the potential energy. This is an abstract Hilbert space problem. We need to choose a realization, a representation. Where are we doing that? So we choose a momentum representation, and in the standard case, in the Euclidean, we have that the momenta operators are just multiplicative operators, and the position operators are displacements or derivatives. And the Schrödinger equation looks something like 4. But then the question, what if I choose another set of coordinates of this? By the way, whenever I say coordinates, I implicitly mean coordinates on the momentum space. If I wanted to talk about the configurational space, I will emphasize it. So I choose a specific set of coordinates, some other p's, which are related to the original one, etas, as given in part. I want to have an isotropic mapping from the twos in order to preserve the rotation. And here alpha has to be some constant, which is in dimension inverse dimension of the momentum. So what happens to my metric? Metric transforms as a tensor given in 6. The position operator is a vector. It transforms like in 7. Here everything is clear. But and here we have a deformed Heisenberg algebra in 8, and it is sometimes argued that this algebra leads to the minimal length or minimal uncertainty in the position, like delta x is greater than alpha or h alpha. One can play with the first of the relations in 8, evaluate from delta x delta p and get that for p, for the expectation value of momentum going to 0, the delta x is always greater than alpha. So it has an upper bound on how precise I can measure spatial distances. And this is then often inferred to say, okay, look, the space is really deformed. We have like a smallest dimension of space. I'm going to argue a bit later that this is wrong in this case. And so the next question is, what happens with the kinetic energy operator? So we know what happens with the position. Then our potential is a function of position. I can transform the potential always. So what is with the kinetic energy operator? So in literature we have seen suggestions that I just simply use p squared over 2m. I choose the new momenta that I have defined as my physical momenta and say that my kinetic energy is p1 squared plus p2 squared plus p3 squared over 2m. But there is nothing special in this form p1 squared plus p2 squared plus p3 squared unless you're living in a flat space with usual Cartesian coordinates. So what I argue is to replace it with the distance squared. So p squared gets replaced to a geodesic distance squared, which is in this case just this h, which was a transformation function, h squared p squared over 2m. Just to remind you, this is the h in 5. This is the relation between the standard canonical coordinates and the deformed ones. So once we are equipped with that, we have a kinetic part, we have a potential part, and we just plug it in our Schrödinger equation. And I consider two specific examples. One is the harmonic potential, potential of the form x squared, and the same will of course applies to any function of x squared. For any potential that is a function of x squared. So the potential looks like this in eta coordinates, but what does it look like in p, in the new coordinates that I chose to call my momenta? Well, it looks like we define it as a divergence of the gradient, because we want to do everywhere consistently covariant. So all the objects appearing in our formalism should have a clear geometrical meaning, and this is what the partial squared or partial eta squared on flat spaces gets replaced, or in standard coordinates gets replaced to on general spaces with arbitrary coordinates. So the expression is this one, 13. So this is one can find this expression in any differential geometry book. So with the choices that we have taken, the Schrödinger equation becomes completely covariant. And but by construction, it is independent of the choice of the coordinates that we take to describe our momentum. So we may just as well choose h equals 1 and the etas as our momenta. So there is no change in the dynamics there. Sorry about that. So, and the energy levels remain the same. There is no change there. What changes is the energy eigenvectors. But since these are scalar functions, they change according to how scalar functions change upon the coordinate change of a certain space. the next is a little bit different, which cannot be reduced to a power law potential of x squared. And this is like, say, inverse Coulomb potential, inverse x potential is Coulomb potential, and so on. This should be in 15. This should be squared underneath. In my paper, I did actually two-dimensional case, so this is why it's linear. So just and yeah, okay, so it's t squared eta. I apologize about that. I mixed the two dimensions, and then in 16 I used three dimensions, but it's the same. So this is the standard action of the Coulomb potential on a eigenvector in the standard case. So this is the simple recipe what changes. So the integration measure changes. You don't have this simple expression here, but when you pass to the coordinates p, you have your integration measure is, as is known, the square root of the determinant of the metric, and then times this Cartesian part. And what will this eta minus eta prime be? Well, that will be just nothing else but the distance between points p and p prime that correspond to this. And this is, yeah, it's a little bit cut, but it goes on to, yeah, it goes h squared, and then there is also p squared. Okay, so yeah, that's more or less it. There's a small note I would like to make about this physical implication, and which I promised before. So, do we have a really discrete space or not? Well, I argue not, because the position operator maintains the same spectrum, and this is a continuous spectrum. Let's say we consider a free particle without potential, then its position operator acting on a wave function. Its wave function is this E or A. It is transformed as a scalar. It allows for a continuum spectrum. There is no true discretization of space. This is in contrast to what will happen when we will really depart from the flat geometry, when we will consider the geometry of the sphere. What concerns this uncertainty relation coming from the deformed Heisenberg algebra, again, here I take the extreme instrumentalist point of view. I just say, okay, what you have here on your new space is that you cannot measure position accurately, but there is no you cannot conclude from that the space itself is discrete. The space remains continuum. It's just that we are limited in this case to measure it arbitrarily precisely. As an analogy, I can always take the canonical case and say design an experiment where I will measure simultaneously position and some function of momentum. Say, I want to design an experiment that will measure position and kinetic energy or something like that simultaneously. What I will get is, again, that delta x will be finite, will be bigger than something finite, not zero. But I cannot conclude from there that the position is truly discrete. I can only conclude that in this type of experiment, I can only measure my position to a certain accuracy. Now we go to a more interesting case, to Snyder's case, where we really have a departure in the geometry from the usual ones. This is then modeled by the equation 19. As we see, we take that our momentum space is a sphere. We actually take only the upper half of the sphere and say, let's take a node pole to be our origin. And we want to describe our, so again, here I'm working in 2 dimensions because as you can see, equation 19 is a constraint. So not all 3 of these etas are physical coordinates. So let's say we take just eta 1 and eta 2 as physical coordinates. Or as in 20, I take the arbitrary definition of my coordinates to describe points on the sphere. These are given by some function, again, h, and now this parameter is beta, no longer alpha. And so again, we proceed as before. We get the metric in 21. The position operator is now interesting. It becomes the angular momentum operator, because the position operator is a translation operator. And when you're on a sphere, it is actually the angular momentum operator.
Recording stopped.
Hello, do you hear me?
Yeah, sure.
Yeah, because recording stopped, it said. Okay. Which then combining this position operator in 22 and the before defined momentum, we arrive at the deformed Heisenberg algebra. We see in 23, this is the usual angular momentum relation, the commutator between angular momentum operators. And the position and momentum get a deformed commutation relation. In this case, again, analyzing this first equation in 23, I get that delta x is greater than beta. But I argue that in this case, this truly is the discreteness of space, the uncertainty in space. So I proceed to define the kinetic energy operator as a distance from the origin, squared divided with 2m. Now some other things are when you do the integration, you again apply this formula, and then for if you want to do Coulomb potentials or those sort of potentials where you have something like this, you change it accordingly to have a geometrical interpretation. And so the final note on here is that when let's say we take one dimension and we choose, so I'm on a circle now, and I choose to define theta, so the angle as my momentum, and my wave function is first I had to show that it's going to be that this is going to be a truly wave function for a free particle. And when this operator, this angular momentum operator acts on it, I get discrete values. So in a sense, to simplify it maximally, I get discrete values of the position operator because the momentum space
Recording
is finite.
in progress.
Because the momentum space is finite. It is the same thing as if I had a finite string, and when I touch it, it has a finite, so it doesn't have a continuum of frequencies, it has like a spectrum of frequency. So this is actually what happens when you truly deform the geometry. You have a finite geometry of momentum space. The direct consequences is that the eigenvalue of the position operator get discrete. So this is truly discretization. How much time I have left? There's maybe a couple of slides on field theory. I don't know if I've already overreached my time.
We have 12 minutes plus 5 minutes for questions.
Oh, okay, great. So, of course, the idea of developing these things is to not to stay at the quantum mechanics level. This is, in a sense, almost like a toy model, because you expect these deformations from the standard usual picture to appear at very, very high scales. And over there, you will not have a non-relativistic dynamics. You will have relativistic dynamics. So the idea is to study field theory on it. And I would like to point out about the body of work by Mir Kasimov and Kadishevsky before all. They developed very, very extensive modifications of field theory in this context. So the one I'm developing here, it's much more primitive. It is I've dubbed this a minimal extension principle. So the theory I introduce is the minimal departure from the usual sense. So having established that this flat different coordinatization of the flat space brings nothing, it's just trivial. We proceed directly to considering curved space. So our energy momentum coordinates will be the surface on which energy and momentum live is described by equation 28. So there are 5 coordinates, as you can see here, but they are constrained. So only we have to choose 4 of them to represent our physical energy momenta. I choose again some momenta small p, which are related to these etas with the function h of the form eta mu will be function h of the p's times p mu. The equation 29 tells us how do momenta add on this space. So if I have 2 particles, one is of momentum p mu, the other is of momentum k mu, and the one particle absorbs the other, then their total momentum is not just an algebraic sum of p mu plus k mu, but it's a rather a complicated expression given by 29 and 30. This expression is non-commutative and non-distributive. So this brings in some interesting consequences for the dynamics. So it's not the same if say an electron of momentum p absorbs a photon of momentum k. That's not the same thing as electron of momentum k absorbing a photon of momentum p, and so on. So as we already said, we just proceed geometrically. So we will have in field theory, we will have in Feynman integrals, we will have to do some integrals over the momentum space, and we will replace the standard integration measure P for P with the generalized one that applies for the general geometry as in 31. There will be also delta functions appearing in vertex factors and so on. So the delta function will be replaced as in 32 with the generalized delta function, which is defined in 33. So just directly as you do in the standard case, you define the delta function in the same way. So I have considered thus far only scalar field theory, described in the standard case by Lagrangian 34. And again, in a minimal way, I replace this Lagrangian in 34 with the Lagrangian in 35. So this p squared, again, which doesn't have a geometrical interpretation, is replaced for general case with the distance squared from the point P to the origin. And the Soviet authors from the 70s and 80s, they have considered much more elaborate deviation from the standard Lagrangian. So this is probably the simplest possibility that one can think. So you can then show that by following exactly the same steps as in the canonical case, you can show that the free Feynman propagator has the form of 36. So in the standard case, instead of d squared, I have p squared, and here is already many times I repeat myself. So the idea is you replace the p squared with the distance squared from the point P to the origin. The causality condition remains the same. It's a plus choice of the plus sign. The vertex factors are usually delta functions in the standard case, and you replace them with your generalized delta functions. Integration over undefined momenta proceeds as in 31. So you replace the integration measure. And what I've shown in my latest paper is that any any amplitude at any order of the perturbation theory, so any Feynman amplitude will always be finite. So I don't know how to calculate it. These expressions are very complicated, but one can convince oneself that at any stage of perturbation theory, you always get finite amplitudes. Even in phi4, which is, if I recall, it was non-renormalizable. And again, the reason is that you have a finite energy momentum space. Once you've done your weak rotation, you sort of get a sphere for energy momentum, and so you by integrating over sphere instead of an infinite plane, you sort of get a natural cutoff there, and this is actually my original motivation in my research. Although in the beginning I said that the motivation is quantum gravity, but I've been doing this for sort of 10 years now, and I've never reached quantum gravity. My motivation is still the original Snyder's motivation, sort of to construct field theory which is finite, which avoids the renormalization altogether. I mean, not altogether, but avoids working with infinite quantities and stuff like dimensional regularization and so on. So to be specific, I've considered this here integral, which is manifestly divergent in the standard case. Because this here integration measure, you will have here p over 3, and then underneath you will have p squared. So this will be quadratically divergent. So here in this setting, we replace as argued before the integration measure, we replace this distance function in the Feynman free propagator. One performs the weak rotation, just the same as in the standard case. You can even do it in this embedding space with where your surface lives. Here one uses the angular coordinates. And with the angular coordinates, the distance and we said the origin, we choose for the origin the North Pole. So, and in the angular coordinates, the distance from the origin will be just okay, since it is not actually a sphere, it is like a sphere with the imaginary radius. So the distance will be imaginary as I times p. P is the radius of this sphere, and omega is the azimuthal. No, sorry, the polar angle. So this is the distance. Once you insert this above here in this expression, you get this expression here. So this is very, I mean, Mathematica returns some 20 lines of sine integrals or whatever. It can be written in terms of sort of elementary functions, but it doesn't matter. It's manifestly finite, and you can get numerically expression like this. So what you get is the amplitude, which is unrepairably divergent. In this formalism, you get that it's finite. So G is here I have as I have written before the charge. And just one more final note. So what you get here is proportional to p squared, and p, as we said, is the radius of this surface on which energy and momenta live. And it is believed that this p scale will be of the order of Planck's scale. So in 39, you're still going to get enormously big number, much bigger than your usual. Now, say you want to find the mass of the electron or whatever. So this expression in 39 will be many orders of magnitude bigger than the usual standard model parameters. So you're going to have to perform the renormalization again. But the difference this time is you don't work with infinities. You don't do stuff like infinity minus infinity is 57, but you always have a finite expression. So this is reassuring. And I think this was my last slide. And I thank everybody for your attention, and please feel free to ask questions.
Thank you, Boris. So let us, Professor Petrov.
Boris, thank you very much for your presentation. Just it reminded me many years ago, it was very active school of Dubna, Kadashevsky, and so on, and they obtained many interesting results. But concerning your talk, there are many questions also, but I limit myself with one only. If you have additional scale, p squared in your case, we know that the dispersion relations, for example, for the scattering amplitude, they are related, were related with possible existence of so-called elementary lengths. And the violation of analyticity on the physical sheet was also related with that. But in your case also, because you have a kind of elementary length as well. So what do you think, in which way maybe reveal the presence of this huge, certainly scale, p square, in the analytical properties of the scattering amplitude?
Well, in this approach that I'm working, this is I don't know. I don't see it personally how it can appear. What can appear is that you calculate some process and then write it as a standard case plus correction, which is of the order of p or p squared, as written here. And then you try to measure deviation from the stand. Of course, it is utterly hopeless at this point, because in order to have to see these corrections, we would have to have momenta of our particles that are taking part in scattering to be near the Planck scale, and we are not able to do this. What I'm working right now actually is I apply this formalism for the statistical physics, and there I do you can, it's just the same, it's the same old recipe. You change the integration measure in momentum space. It's anyway only these momentum integrals that are appearing, and then you will have corrections that will be of this, say, p squared, this scale, but this will, oh sorry, it will be the temperature times the momentum divided with this p squared. And this gives hope that in the early stages of the universe, when the temperature is very high, you can get some, you can sort of maybe see in the cosmological remnants some signature of this. Another option is, of course, to have very large masses, elementary particles that are not discovered but that have very large masses, such as some dark matter particles, or is this was also done by a Russian scientist called Markov. He postulated this existence of maximums. This would be the elementary particles with the maximum allowed mass, but the geodesic distance is pi half times this scale p. So for them, you could maybe see these effects. But in analytic, just to go back to your question, no, I don't see in analytical properties how I would see this effect.
Okay. And if there are any people who want to ask something, because I have also the question. No?
No questions? No more questions.
Okay, then I can add some. I have to ask some kind of technical question. If you leave intact the coordinate space, and then how you have the substitute for that Fourier transform? You just put, instead of Kronecker symbol, you put your GIG of P, or not?
Yeah, this is a technical issue. I think in these cases, those things are called Gelfand-Greif Fourier transform or something like that. So I did not study it. I actually quite how to say smoothly avoided this question altogether, because you can see I have reached the momentum space formulation in the standard case before introducing any geometrical or coordinate deviations from the standard case. And once I have a formulation of dynamics in momentum space, this is the point where I attack. I just say, okay, let's make it covariant. Let's make it. So I never really have to do the Fourier transform on this space, but the thing has been considered. Yeah.
Thank you. Thank you. Thank you very much.
More questions? No? Dr. Ivetic, thank you again.